Hi everyone, and welcome to the 3.5 day 1 video. Let me tell you right now, this is going to be a long video, probably more than 30 minutes. We are going to be going over problems 1, 3, and 4, but this is also 2 days worth of material, so feel free to pause this partway through, go back, watch it again, watch at double speed, do what you need to do. Anyway, let's get started. So this first paragraph right here is talking about rational functions, the p of q over q of q, and we are looking for, let's see. The zeros of a rational function occur when p of x is equal to 0. Remember, that's going to be our numerator. That is, the function's value is 0, where the value of the numerator is 0. And then a rational function undefined when q of x is equal to 0, or denominator, as the function is undefined whenever its denominator is 0. The only exceptions to these, when it's not a 0 in the numerator, is going to be, where is my pen? When we are talking about wholes. So I mentioned that in the last video as well, but I just wanted to make sure I brought it up again. But the next question is, the long-run behavior of r of x can be defined by the ratio of the leading terms of p and q. So we have a question right here that says, determine the long-run behavior of the following functions. Now, if you'll remember, the long-run behavior was in fact connected to horizontal asymptotes. That's a z. So that's going to be connected to horizontal asymptotes. Now, in the last video, we were dealing more with like the transformational form of a rational function, so a little bit more like what you see in function A over here. But now we're going to be dealing more with polynomial form, where we have an x on both the numerator and the denominator. So there's actually 3 different things that's going to determine a horizontal asymptote here. Or not 3 different things, just 3 different situations we could be talking about. So what I'm going to do is I'm going to fill out notes on the right side of the screen and then do some of the examples on the left side. So we're really going to be looking at the degree of the numerator and the denominator. So if the degree of ... so that's like going to be the beginning of each of these kind of bullet points. So first bullet point, or first situation, is what if the degree of the numerator is less than the degree of the denominator. So remember, this isn't the numerator being smaller, it's the degree of the numerator being less than the degree of the denominator. Well then, your horizontal asymptote is y is equal to 0, simple as that. So if we take a look at problem A here, there is actually no x in the numerator, but you can think of this as like x to the power of 0, since anything to the power of 0 is just 1. So let's see, the numerator here, this degree is 0, this degree is 2, the degree of the numerator is less than the degree of the denominator. So we can just say the horizontal asymptote, y is equal to 0. And we can do the exact same thing for problem B. So this is 3x to 3x minus 5, or 3x to the power of 1 minus 5. And then in the denominator here, I can see that the degree is 2, meaning that, hey, since the degree of the numerator is less than the degree of the denominator, we can say that the horizontal asymptote is y is equal to 0. Now, we're not just looking for the horizontal asymptotes, we're also looking for the long-run behavior. So the cool thing is that no matter what, in this situation, the long-run behavior is always going to be the same. So for this case, our long-run behavior is always going to be as x approaches negative infinity, r of x or f of x approaches 0. And as x approaches infinity, r of x approaches 0. So that's going to be the long-run behavior for both of these examples. Remember that long-run behavior is connected to the horizontal asymptote. So that's going to be our first example. Our second example, or situation, is if the degree of the numerator is equal to the degree of the denominator. Then what happens? Well, if the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is the ratio of the leading coefficients. Now that may sound kind of like a lot, like, wow, it's the ratio of the leading coefficients. What does that mean? Well, if we take a look at example C over here, I'm going to notice that we have an x squared up here and an x squared up here, saying that, hey, both the degrees are the same. So if I take a look at their leading coefficients, or just the numbers farthest out in front, we kind of have an invisible 1 here, an invisible 1 here. So if I want to take the ratio of those, I'm just going to do 1 over 1. And we can say that the horizontal asymptote here is y is equal to 1. So in this specific case, the long run behavior is going to be, as x approaches negative infinity, r of x approaches 1, and as x approaches infinity, r of x approaches 1. So it's really whatever that horizontal asymptote is. So in general, you can think of the long run behavior for this problem, or this type of problem, as x approaches negative infinity, r of x approaches, I'm going to say, quote unquote, the ratio, just really whatever you found. And as x approaches positive infinity, r of x is still going to approach the ratio, or whatever that means. So we really have one more situation left, and I'm hoping that you can guess what it is. But our last situation is if the degree of the numerator is greater than the degree of the denominator, what do you do? Well, in this case, you don't actually have a horizontal asymptote. So if the degree of the numerator is larger than the degree of the denominator, there is an oblique, or you're going to hear me say slant asymptote. And the equation for the slant asymptote can be found using polynomial long division. Now, here's the thing. Looking at things to cut for this unit, we are in fact cutting the polynomial long division. So there's going to be a bonus video later on that is your choice to watch, going through how to find a slant asymptote and understanding that how to find that equation and doing the polynomial long division. However, I'm not going to test you on that. What I am going to test you on is identifying that there is a slant asymptote. So for instance, if I take a look at part D and I see, okay, in our numerator we have a degree of 2, and in our denominator we have a degree of 1. In this case, we're not going to have horizontal asymptote. So horizontal asymptote, none, y is a slant asymptote. That is what I will be asking you to do on the test. So I'm asking you to identify if there's a slant or oblique asymptote, and just knowing that there's not a horizontal asymptote. I will not have you solve for it. That will be in the bonus video if you choose to watch it. Don't worry about example E. Example E is just if the degree of the numerator is more than 1 degree larger than the denominator. And essentially things just go to infinity. But you know what? Don't worry about it. So I'm hoping all of this seems vaguely familiar from what you've done in previous math classes, but I want to put this to the test. So we're going to be taking a look at pages 3 and 4 in the notes and just going through those entire problems. So let's come along for the ride. So if we take a look at, there we go, if we take a look at example 3, it's going to ask us to do a lot of things. So we have our r of x already stated, and we're going to need to factor and simplify, state the domain and any holes, find the long run behavior, any horizontal asymptotes, determine if it crosses the horizontal asymptote, which is something new we'll be talking about. We need to find any vertical intercepts or any y-intercepts. We find any zeros, any vertical asymptotes, And the last thing it says, state the behavior of a function around the zeros and the vertical asymptotes. It's not asking about multiplicities, it's just saying, hey, what are the points around it? So we are also going to be making a table and graphing. So this is what one really long problem looks like, but all of this is kind of stuff that we've done before, so let's just get to practicing. So I'm going to zoom in a little bit just to make sure we have enough space. So let's see. We have that r of x is equal to 3x minus 6 over x squared plus x minus 6. Now the first step says to factor and simplify, so that's what I'm going to do. I take a look at that numerator and I see that I can factor out a 3. So I get 3 times x minus 2. And in my denominator, I'm looking for two numbers that multiply to negative 2 and add to 1. Pardon me. The negative 2 is a spoiler. Multiplies to negative 6 and adds to 1. So that is going to be x plus 3. Then there's the x minus 2. Oh, and you'll notice we have something in common. Something does cancel out. It's going to be those x minus 2's. Lovely. So when we cancel those out, we're going to be left with 3 over x plus 3. And this is the problem that we're going to be using throughout the rest of the equation, the rest of the problem. The only thing we're going to need that x minus 2 for is to figure out the whole. So that's the next piece we're going to do. So for our whole, oops, here we go. So for a whole, you're going to take the x value of that whole, plug it into the equation, and solve. So for us, since we have a factor at x minus 2, I set that equal to 0, we got x is equal to 2. So we'll find r of 2, so that's going to be 3 over 2 plus 3, which is 3 over 5. So we're going to have a whole at the point 2, 3/5. So we're going to have to remember that for later. Let's see. Next, let's find our domain. That's the next thing that it asked for. So I'm going to be looking for any restrictions that we may have. So the first restriction is this whole that we're talking about. So again, I'm just going to say, hey, x minus 2 is equal to 0. Okay, so we're going to have a restriction when x is 2. And the last one, I'm going to look in the denominator and say, hey, x plus 3, we don't want that to be 0. I'm going to cross these out. So we can say that, hey, x is not going to be negative 3. So we found our restriction, I'll highlight these, at positive 2 and negative 3. So we write our domain, that's going to be from negative infinity to negative 3, and from negative 3 to 2, and from 2 to infinity. So just a reminder, this break right here, that's going to be from our denominator, and that's going to be our vertical asymptote. We'll talk about that a little bit more later. And then at 2 right here, this is where we're going to have a physical hole in the graph. So that's where those restrictions are coming from. Anyway, that was the whole first bullet point. Hopefully that went okay for you. Next, we're going to be looking for the long run behavior. And remember, that's connected to any horizontal asymptotes. So first, let's find that horizontal asymptote. I'm going to look at my equation over here. Now remember, I'm going to be looking at the degree of my numerator, the degree of my denominator, and compare those. So if I look over here, I can say, you know what, there's actually not anything up here. So you can think of this as like an x to the power of 0, or if you want to go back to the original problem, you don't have to do that, but if you want to go back to the original problem, you can say, hey, in this numerator, this is 3x to the power of 1, and this is x squared. So I can say the degree of my numerator is less than the degree of my denominator, which means that my horizontal asymptote is y is equal to 0. That's it. You don't have to solve for anything. I'm just going to make a comment that we know that because the degree of numerator is less than the degree of the denominator. That's why we're saying that. You don't have to write that comment. I'm just doing that for fun. But that's really going to help us with our long run behavior. So for our long run behavior, I know that R should be capitalized from capitalizing everything else. I never know when to capitalize the R. Okay, so for us, we're going to have as x approaches negative infinity, r of x approaches whatever our horizontal asymptote is. In this case, 0. I got muted. Sorry, y'all. My hand hit the thing. As x approaches infinity, r of x still approaches 0. So that's most of the second bullet point. The last part says determine if the function crosses the horizontal asymptote. So here's the thing. Asymptotes are these boundaries we're not allowed to cross, except there's always an exception for everything. So for a horizontal asymptote, you actually can cross a horizontal asymptote. Because what we really care about with the horizontal asymptote is a long run behavior, which is what you kind of look at where the ends are going if you zoom way, 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 way out. And if you zoom way, 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 way out, what's happening in the, the finer details doesn't really matter. So the function may cross the horizontal asymptote once or twice, and that's okay. So the way we check for that, and we're going to call this the horizontal asymptote intersection point. The way we're going to check for this, and I'll write this in green, you check by setting the function equal to the horizontal asymptote. Or basically what you're saying is that if you take the horizontal asymptote, or that y value, and you set it equal to the function, are you going to get an x value? Because if you set it equal to a y value and you get an x value, there's going to be a point there. But if not, then it's not going to cross anywhere. So let's check. There we go. Oh, I am running out of space. Okay, so I'm going to thank you for being patient with me so we can keep all that in there. Yes. So I'm going to take my horizontal asymptote, which is 0, set it equal to my function, of 3 over x plus 3, and then try and solve. So I'm going to multiply both sides by x plus 3, and I get 0 is equal to 3. And we've come across this example quite a bit. We know that 0 does not equal to 3. That's not a real thing. So if we come across something like this, there is no intersection point. No intersection point. So you don't have to worry about it. Few more things. That was the second bullet point. Third bullet point is just finding the vertical intercept, or the y-intercept. That's kind of nice. That's going to go pretty quick for us. So our vertical intercept, ooh, I might end up going off the page here, is we're going to plug 0 in, so 0 in for x. R of 0 is going to give us 3 over 0 plus 3, or 3 over 3, which is equal to 1. So we're going to have a vertical intercept at 0, 1. Very cool. So it was the third bullet point. Last bullet point is going to ask for any zeros or horizontal intercepts and vertical asymptotes. So for our horizontal intercepts, as you might remember from our last video, we just take the function, set it equal to 0, see if we have anything that works. The cool thing is we've kind of already done that because that's where we have our horizontal asymptote. And so if we've already done the work, you can just refer back to another problem. So for instance, I'm just going to write a note here that says horizontal intercepts, none, see horizontal asymptote, intersection point. Because if we don't cross anywhere where the y value is 0, that means we're not crossing the x-axis, so you're not going to have any zeros or horizontal intercepts. Let's see, lastly, we're going to have our vertical asymptote. So if we take a look in the denominator, and I'm just going to point over here to our function, x plus 3, if we set the denominator equal to 0 and solve, we're going to have a vertical asymptote at x is equal to -3. And you can also see that work when we solve for the domain. So, here are all of our features. We still have to graph this. That's why I said this video might be longer than 30 minutes. So I'm going to make a table. Just like we did with polynomials, I will give you the table, so you don't have to worry about that. But I'll let you know what I do is I usually do 3 spaces, and then whatever my asymptote is, my vertical asymptote. So -3, that's going to be undefined because that's my asymptote. And then I usually do 3 more x values around that, just so I make sure I have an even amount of work on either side of my asymptote, and then I'll include any other points I need. So from here, I'm going to count backwards. We're going to go count backwards half a space, so negative 3.5, and then we'll go negative 4, negative 5. We'll count forward half a space at first, so negative 2.5, then negative 2 and negative 1. Now, there's 2 other points we want to include. We haven't included our vertical intercept yet, or when the x value is 0. And then we also have a point from the very, very beginning. And that's going to be our hole. So we're going to want to make sure that we include that hole. The y values that we already know is that when x is 2, y is 3/5. And when x is 0, y is 1. Everything else, we would take these x values, plug them into our equation of 3 over x plus 3, and solve. I'm just going to give you the answers right away. I have a negative 1.5, negative 3, negative 6, 6, 3, and 1.5. Now let's graph these points. First thing I'm going to do, let's graph my intercept. So, pardon me, not my intercepts, my asymptotes. So we're going to have a vertical asymptote at x is equal to negative 3. Got a boundary here. We also have a horizontal asymptote at y is equal to 0. Now let's plot these points. So let's see, negative 5, negative 1.5, negative 4, negative 3, negative 3.5, negative 6. So that kind of tells us this behavior right here. Connect that to the best of my abilities. And then let's see, negative 2.5, 6, negative 2, 3, negative 1, 1.5, and then remember we have other points we have to include. So here's our y-intercept, and then this point right here, remember that is a hole. That has to be a physical open point. So that's going to be at about right here. So you want to make sure you make that an open point. And then when you connect your graph, don't draw through it, because then it's no longer an open point. So I kind of like to start from the hole and then continue onward. So this is what our graph looks like. We have found so much information on it. Look at this. Isn't this beautiful? Let's do this once more. Thank you for sticking with me. Feel free to pause and go grab a snack. Let's move to page number 4, example number 4. We're doing all the exact same things. It's got the same bullet points. So we're going to start by taking our r of x. Oops, that's still green. Did not realize that. Let's change that to blue. R of x is equal to x squared minus 5x minus 6. We're going to factor this. We're looking for 2 numbers that multiply to negative 6 and add to negative 5. And that's going to give us x minus 6 and x plus 1. This is not going to be x minus 2 and x minus 3, because a negative 2 times a negative 3 gives us a positive 6. And then in our denominator, we're looking for 2 numbers that multiply to negative 12 and add to 1. And that's going to be x minus 3 and x plus 4. So I factored, I looked at this, nothing cancels, so I've already simplified. So if we're looking for holes, well, if nothing cancels out, how many holes are there? There are none. There are none holes. Awesome. So let's take a look at our domain. For our domain, I need to see if there's any restrictions. And we're going to have those restrictions if we take a look in the denominator. So I'm going to set each of these factors equal to 0 and solve. So starting with x plus 4, I'm like, hey, that can't be 0. That's bad. It means that x cannot be negative 4. And if I do the same thing with, that's x minus 3 not being equal to 0, we're saying, hey, x cannot be 3. So if we look at our domain overall, we're going to have 2 different breaks in there. So it'll be from negative infinity to negative 4, and from negative 4 to 3, and from, oh my goodness, I keep doing that. There we go. And from 3 to infinity. So remember, all of these breaks here are coming from vertical asymptotes because they're coming directly from our denominator and nowhere else. And we will write that down later once we get to our vertical asymptote. Then anyway, bullet point 1, done. Next, we're going to take a look at our horizontal asymptote and our long run behavior. So for our horizontal asymptote, we're going to take a look at the degree of the numerator and the degree of the denominator. So if I go back to my original problem, I'm going to say, hey, look, they're both squared. So the degree of my numerator is equal to the degree of my denominator, which means I'm going to take a look at their leading coefficients, so 1 and 1, and I'm going to find that ratio there, so 1 over 1, meaning my horizontal asymptote is y is equal to 1. There we go. And remember, we found that because the degree of the numerator is equal to the degree of the denominator. Okay? So if we want to find our long run behavior, and I'm just going to shorten that to LRB, if we want to find our long run behavior, we're going to say that as x approaches negative infinity, r of x approaches whatever our horizontal asymptote was, so in this case 1, and as x approaches infinity, r of x still approaches 1. There you go. So now that we've done our horizontal asymptote and our long run behavior, we have to see if there's anywhere on the graph where, there we go, where our graph crosses the horizontal asymptote. So we're going to call that the horizontal asymptote intersection point. And remember, we're going to find that by setting r of x equal to 1, and we get that directly from a horizontal asymptote. And we're going to solve for x. So let's do just that. So if we take our horizontal asymptote of, or let's see, let's take our function first. Let's take our function, and I'm going to take the original one here. You can do either one. I just know we're going to have to multiply things out in the end anyway, so I'm just going to keep our already multiplied out version. And I'm going to set that equal to 1. So from here, I'm going to multiply both sides by the denominator. So x squared minus 5x minus 6 is going to be equal to 1 times the denominator, or x squared plus x minus 12. Let's see, I'm going to subtract x squared on both sides, and that's going to leave me a negative 5x minus 6. Don't drop that negative sign. Is equal to x minus 12. From there, I'm going to subtract x on both sides and add 6 on both sides. So I get all my x's to one side, all my numbers to another. I'm going to get negative 6x is equal to negative 6. If I divide both sides by 6, that gives me x is equal to 1. So what this means is, okay, we found an x value for this y value. It does cross at a point. So we can say the intersection point for the intersection is located at 1, 1, since we set it equal to 1 originally and we found that the x value is 1. So at this point, our graph is going to cross the horizontal intercept. So that's kind of how we double check. Anyway, all of that was our second bullet point. Our third bullet point was taking a look at our vertical intercepts. And this one you can use either the factored version or the original version. I think I'm just going to use the original version because that's what I have on my notes from last year. Ooh, there we go. So let's see, it's going to be r of 0, plugging 0 into the equation. So it's going to be 0 squared minus 5 times 0 minus 6 divided by 0 squared plus 0 minus 12. A lot of things go to 0, and we end up with negative 6 over negative 12, which is the same as 1/2. So we're going to have a vertical intercept. My hand keeps pressing the mute button. I am so sorry. I'm just going to keep on going. It takes a lot to edit these, so thank you for bearing with me. Let's see. We got just a couple more pieces to find out. Let's do the horizontal intercepts next, or our zeros. So for our horizontal intercepts, you can set the whole function equal to 0, which is what we've been doing, but you may notice that there is a bit of a shortcut. You can just set the numerator equal to 0, because you're always going to multiply by the denominator on both sides, and 0 times that denominator is always going to be 0. So I'm just going to take my 0 and set it equal to just the numerator. And I'm going to use the factored version this time, because this is going to help me solve. So I'm going to say that, hey, x minus 6 is equal to 0, and x plus 1 is equal to 0. So if I want to find my actual zeros, I'll solve for both of these and get x is equal to 6, and x is equal to -1. But since this is an intercept, I want this as an actual point. So this is going to be 6, 0, and -1, 0. And then one of the last things for this bullet point is our vertical asymptotes. Now we've actually already done the work for this when we did our domain, if you'll remember, where we set the denominator equal to 0, we solved, and we get, let's see, that our vertical asymptotes, we got x is equal to -4, and x is equal to 3. So we get to here, and it's like, okay, we have found all of our features. The last thing we need to do is make a table. This table in particular is going to be really, really long, because I want 3 points on either side of my vertical asymptotes. And since we have 2 vertical asymptotes, I'm also going to need all the points in between there. So I'm never going to have you graph something this big on, or something with this many points on a test, so don't worry about it. I just wanted to show you what this looks like, because I think this is going to look pretty cool. So it's going to be 3 spaces. And then my first asymptote, and that's going to be at -4. And so if we count backwards, we'll do -4.5 to keep that half point, -5, and -6. We'll go forward 3, so -3.5, -3, -2. And I'm also going to want all the points in between or all the whole numbers until we get to our next asymptote. So we're also going to have -1, 0, 1, 2. I'm going to throw in a 2.5 because our next asymptote is at 3. And then I want 3 numbers on either side of that. So 3.5, 4, and 5. And then we have an x-intercept, so I'm going to include that at 6. So again, never going to have you do anything this big on a test. This is just, because I can. So I'm going to take all these numbers, plug them into our equation. It's going to be really long. You're going to get lots of decimals. Remember, when you're doing a table, you only have to round to the first decimal place. This is not where we need it to be exact. So I'm just going to give you the values here. We're going to get 3.3, 5.5, 9.8, which won't fit, but that's okay. -7.3, -3, -0.8, 0, 1/2, we already have that from our y-intercept, 1, 2, 3.8, -3, -1.3, -0.3, and 0. So these are going to be a lot of points. Feel free to take a look at the completed notes for this page. The table and the graph will already be there. Anyway, let's graph what we know. So we know we have a vertical asymptote at x is equal to -4. We have another one at x is equal to 3. We have a horizontal asymptote at y is equal to 1. We're going to have a y-intercept at 0, 1/2. We're going to have a horizontal intersection point at 1, 1. And we're going to have 2 horizontal intercepts, or x-intercepts, one at -1 and one at 6. So these are all of the points we know. I'm going to graph all of the other points that are not on here. So I'm going to actually pause right now, do them all, and then press record again, and so you'll just see once the points are already in there. All right, so I just graphed all of the points that are on our table. And so we're actually going to have three sections here. We're going to have this one in the topmost section. It goes something like this. We don't see a whole lot of that. We really get to see a lot of this middle section, and it's actually doing kind of a cubic thing, which I think looks pretty cool. And then our last one, we do have a few more points. Whoop. Notice that I'm always going from one end of the graph to the other. I'm not stopping anywhere, and I'm going through as many points as possible. We don't have any holes, so I don't have to worry about this. I just thought that this problem had a lot of really cool features to it. So the graph looks cool, and if we take a look at all this information, oh, so much good stuff. So please practice the practice problems we'll do in class. I'm going to give you another set on Wednesday, and I'll kind of explain what I want you to do there. I hope you enjoyed the video. I'm sorry it was so long.